So we're going to do some harmonic motion examples. This is the first one that I did with everyone. It's about the Ferris wheel. So just to make clear what's going on and repeat what we've said in class. So you have a Ferris wheel that has a radius of 100 feet. So you can go ahead and label everything. Go ahead and draw yourself a picture. That's the best way to understand many of these. So from the center of the Ferris wheel, which I've already drawn, is 100 feet. Okay. It makes one rotation every 30 seconds. So one full time around lasts 30 seconds. Okay. The center of the wheel is 105 feet above the ground from the center to the ground, right? There's the ground down there is 105. And it says to write a sinusoidal equation of the person's height above the ground. Assume uniform speed from beginning to end of the ride. The person is at the center. So the person's somewhere here at the center, right? Here's your person. And which way are they rotating? We're just going to assume positive rotation just for our sake. It could be going in the other direction, but we can model this any way we want to as long as they're at the center and moving up. They're headed up when it begins, so they're going in this direction. So what is this going to look like over time? You are going to model the person's height over time. What's happening to the person's height? So what is the highest that this person will reach? Well, it's 105 feet above the ground and another 100 feet above that. So it's going to be 205 feet here. The middle line here is at 105. That's where the person is at the middle, moving up. And then the lowest point will be, right, if the radius is 100, so 105 minus 100 would be 5 feet above the ground. So you're going to measure this person's height over time. So I'm going to break this out into quadrants. So as the person's at the center, they're right here. Let me get another color. They're right here. Okay. And they're moving upward. So in the first quadrant, they're at the center and they're moving up to the maximum height. Second quadrant, they're moving from the maximum down to the middle here. So over time, this is what their height is doing. And then at the center to the minimum of the Ferris wheel, so third quadrant. And then fourth quadrant from the minimum back up to the middle. So that is what your person's height, this is the person's height. Think about what's happening. This is the guy on the right going up, down to the minimum, and then back up again, which exactly models a cosine wave. Well, guess what? This is one cycle of a cosine wave. That's all we need. How long does it take? This is the time going in this horizontal direction. So one cycle around takes 30 seconds. Okay, so if you start at time equals 0, it didn't say anything else about the time on here, so we're just going to assume time equals 0. At the end, it's 30 seconds. Okay, that 30 seconds is going to be split up into 4 pieces, right? Half of 30 seconds, right? Halfway through the ride, one cycle of the ride, it's 15 seconds. Halfway through that is 7.5. And then 30 minus 7.5 would give you 22.5 there. All right, so the first thing you need to do when you have a harmonic motion problem is model it with a graph. From the graph, you can deduce many things here. You can create an equation based on this graph. Okay, so another thing is, so let's do that. Let's write the equation. It's a sine wave. So we take our standard equation like this. A is the amplitude. So that is right here or here. Okay, so that would be a 100 sine. Now the B can be determined from the period. This is the period constant. It is not the period. The period is how long it takes one cycle to go. So what is the period? 2 pi over B, or if you're looking for B, B is equal to 2 pi over E. Do your algebra. Okay, what is the period here? In this case, one time around, that's one cycle is a period. So that would be 2 pi over, what does it take to go around one time? 30 seconds. Okay, so you end up reducing that fraction, divide by 2, numerator, denominator, you get pi over 15. So there's your B, just plug it in there. Then x minus the start, which happens to be 0, plus your vertical shift, which is here at the midline, 105. All right, let's try another problem. Here we have Mars rotating around the sun. Its distance varies from 205 to 249 kilometers. After 0.2 years, Mars has reached its maximum distance of 249 million kilometers from the sun. Okay, so we have potentially, let's see if I can draw this. Here's the sun. Again, we have rotation going around here, and here is Mars rotating around the sun. It's kind of a wonky rotation there, okay? So its distance varies from, so you have to think of maybe more an elliptical motion. Okay, sometimes it's closer, sometimes it's farther. All right, so it says after 0.2 years, it reached its maximum. So people. The way you determine what you can draw a sine wave, a cosine wave, a negative sine wave, or a negative cosine wave. Any one of those four. You do not know where Mars is when you start looking. It could be anywhere in its cycle. It might be in a very inconvenient place, like right here, possibly, or right over here, somewhere weird that does not reflect a very convenient spot to start on a sine or a cosine wave. However, if you're watching, it's like watching a runner on a race, right? Maybe you want to time them after they go past a certain marker on the track. Okay, now I'm going to start looking at them. All right, this is the same thing here. After 0.2 years, so again, time is telling you about the phase shift. When does it start, the time? After 0.2 years, it's at a maximum. Okay, so that would tell you any type of wave that's at a maximum is a cosine wave. If it's at a minimum, it would be a negative cosine wave. If it's starting at the middle, headed up, like the Ferris wheel, that would be a sine wave. And a middle headed down, that would be a negative sine wave, excuse me. Okay, so here we're talking about a maximum. So that is where it is convenient for you to draw one cycle. Okay, so let's go ahead and label this a little bit. Let's make some quadrants there. Okay, so they are talking about Mars being at a maximum right here. All right, so you're going to start the wave here, right? And then it's going to move down towards the middle. That was the first part of its rotation. And then it's going to move to the minimum. And then from the minimum to the middle. Over time, right? This is time here. And then from the minimum back up to its original spot where you started looking after 0.2 years. Okay. And you know the maximum distance is, it tells you, 249. And it varies from 205, so that's going to be its minimum. 205, right? This is the distance here, distance on this axis right here. Okay, so what's halfway in between that? Let's say 249 minus 205 divided by 2, right? Halfway in between, so it's 22 in between. So 249 minus 22 is 227. Okay, so there's the max, the middle, and the minimum. And you know, on top of that, that one whole rotation, it says, takes 1.8 years to rotate around the sun. One rotation is the period. So you know the whole one time around the sun is 1.8 years. So this is like, again, think of a bank balance. If you're starting at 0.2 years, where it is convenient for you to start because you have a nice cosine wave represented then, not something that's starting here and ending here, right? You're not looking at a weird piece like that, okay? You are looking at a nice cosine wave that starts here at a max and ends at a max, okay? You look at the bank balance, like think of it like that. 0.2 years is when it's at the max. And then 1 year later, it will be at 0.2 plus 1.8, which is 2 years. Okay, so now all you have to do is divide that 1.8 up into 4 pieces. You have these 4 quadrants. So how long does that take? 1.8 divided by 4 would be 0.45. In each of these quadrants. 0.45 times 4 adds up to the entire 1.8, but we are just trying to find out where is this Mars distance from the sun in each of these critical points. That's why we're doing that. So 0.2 plus 0.45, that would be at 0.65 years here. Okay, plus another 0.45 is 1.1. Plus another 0.45 would be 1.55, plus another 0.45 should equal, let's see, 1.55 plus 0.45 should equal 2. Yes, it does. Okay. All right, so now we can determine an equation. This is modeling a cosine wave because that's what was convenient for you. It is a model. You're trying to get something that can tell you to help you make predictions. Okay, so that was what was convenient because they talked about starting at a maximum. All right, so here's your cosine standard equation. Okay, so what is the amplitude? We determined to be 22. Remember, amplitude is always between the midline and the max or the midline and the minimum. So that was 22. Cosine B, determined by the period again. So remember, if you did your algebra, it would be 2 pi over E. What is E? E is 1.8. So here's B is equal to 2 pi over 1.8. I'm going to do something a little bit algebra fraction-like. Okay, divide the numerator by 2, you get pi. To divide the denominator by 2, you get 0.9. Okay, I'm going to go up here. Pi over 0.9 is the same as pi over 9/10. Okay, and you multiply by the reciprocal on numerator and denominator. So you get 10 pi over 9 for B. Now, people get confused from the pi because it seems too abstract for them. It's just a number, just like with degrees, it's just a number, okay? So this B helps to determine the period, all right? 10 pi over 9. You know the period already, though, so we're working backwards. So you either know the period and you find the B, the constant, or you know the B and you can find the period, one way or the other. Now, X minus the start. What's the start? 0.2 years, plus D, which is the vertical shift, 227. Now, at any one time, you have to kind of draw a graph here. From the graph, you can determine the equation. And from the equation, now you can model where Mars is any point in time, at any point in time. If you said, where is Mars? What is the distance of Mars from the sun after 22 years? Guess where you're putting in that 22? Right here. Stick in your 22 in there, plug it into your calculator using radians in this case, okay, radian mode. And then you can find exactly where Mars is going to be on this trajectory here. Is it going to be 227 million kilometers from the sun? Is it going to be somewhere in between there? But it's going to be somewhere in between 205 and 249 million kilometers from the sun. You can predict with this model at any time. Okay, let's try another example. So we have the population of predatory animals that vary periodically with time. Again, harmonic motion, it is something that varies its distance or its population or its number over time. Okay, so we're talking about now fox population in a certain forest varies sinusoidally with time. Records started being kept in 2003, which we will call T equals 0. So the thing is about that, people, at T equals 0, we do not know what's going on here. What if T equals 0 is right here? Sorry, that's probably a bad example. I didn't draw that very well. Let's say here's the fox population varying over time sinusoidally. And when you happened to look, it was like right here. That is not a very convenient place to start a wave. Do you want to keep going from here to here? That's one cycle of that wave, from here to here. It looks a little bit like it's close to a sine wave, but it's not quite. It's off, okay? So what they want you to do, here, let's read on. Assume the population varies sinusoidally. Records start being kept. This was T equals 0 at a kind of a weird spot on the wave, okay? But then they noticed a maximum number of 800 here, a maximum started at T equals 0.9 years. That is when it's convenient because now you can look at a nice clean cycle of a cosine wave right here from a maximum to a maximum instead of this weird off wave here. What you want is, like I said, a positive cosine, which is a max, a negative cosine, which could be a min. They didn't talk about a min, they talked about a max. Okay. Or positive sign or negative sign, which starts at the middle moving upwards or middle moving downwards. Those are the 4 cases that you want. That's what the phase shift does for you. It tells you like, okay, this person is running around the track or whatever, but this is when it crosses the start line and I'm going to start my clock there instead. All you got to do is say, okay, there's the phase shift. All right, so let's erase this now. And then go ahead and graph this out. Okay, so we have always the max, the midline, the min. We're looking only at one rotation, people. We do not need 200 cycles of this, even though that's what's going on. If you're using your calculator or some other tool to help you out, and that's what you're doing, I can tell that you don't know what's happening. Okay, we just need one cycle here. So again, it said it was starting at a max. And here it says 800 foxes at the max. And that started at t equals 0.9 years. So again, this is time. Going in this direction, this is fox population. Okay, so it was at a max. Go ahead and draw your cosine wave, a max in each quadrant. This is what's happening. You need to be drawing nice cosine waves, not one of these. That is not nice. That's not a cosine wave. A cosine wave is not an absolute value function. It's not a sharp function like that, okay? Then it says the next minimum, okay, there is a minimum of 200 foxes, so that we know. Just one thing at a time, people, okay? Let's just do one thing at a time. It said the minimum occurred, so here, you started at the max, and it said at the minimum was t equals 1.5 year. Okay, so this is 1.5 right here. So if you know when when it started at the max, that's the beginning of your cycle, to this is telling you how much half a cycle is. Half a cycle. So 1.5 minus 0.9 would be 0.6. Is that correct? Which means it is 0.3 every quadrant here. 0.3 plus 0.3, right? 0.9 plus 0.3 plus 0.3 should equal 1.5 plus 0.3 plus 0.3. That will give you every single critical point here, each of these critical points. Okay, here, so you can see it better. These critical points. Okay. All right, so 0.9 plus 0.3 is 1.2. 1.2 plus 0.3 is 1.5. 1.5 plus 0.3 would equal 1.8. And 1.8 plus 0.3 would equal 2.1. Again, 0.9 all the way to here gives you one period. Okay, so 2.1 minus 0.9 would equal 1.2. One whole cycle. So again, people, even if this is what's happening with the fox population, it wouldn't matter where you started. If you started at the weird spot that they told you, like here, and timed it for one whole cycle until here, that period is still 1.2. No matter if you go from the max to the max or the min to the min, it doesn't matter. All of those cycles would be 1.2. You are just modeling a situation conveniently for you so you can create after this an equation which you can use at any time to determine the fox population at any point in time. Okay, so let's finish this out. 800 to 200 of the fox population, right? What's halfway in between that? Let's see, 800 minus 200 is 600. That means it's 300 here and 300 here, right? 800 minus 300 would be 500. 500 minus that 300 would be 200. So there you go. Now we can start modeling this equation. We can start writing an equation for this. This is a cosine wave. So we will have the standard coastline model. Okay, so A is the amplitude, which is this or this, either one, 300. Cosine B, again, is determined from the period, 2 pi over the period, which you now know. The whole cycle, one whole cycle, no matter where you start it, one cycle will be 1.2 years. Again, I'll do a little fraction work here. Divide by 2 on the numerator would be pi. Divide by 2 on the denominator would be 0.6. And that's the same as pi over 6/10. Okay, and then multiply by the reciprocal. That gets rid of the entire denominator, so that would be 10 pi over 6. Pi times 10 divided by 6. Okay, and then reduce that out, so that would be divided by 2, 5 pi over 3. Okay, so 5 pi over 3, then x minus the start, which is 0.9, plus the vertical shift, which is 500. Okay, and this equation right here will model your fox population at any point in time in the whole history of planet Earth for this forest. So where do you put, like, what is the fox population at t equals 22 years again, or 25 or 100 years from now? Where do you put that? You put that 100 years in here, and that will model your fox population. It's going to be somewhere in between 200 and 800 fox. Okay, let's try another one. Again, you can pause anytime here or fast forward if you already understand some of these, or skip it altogether. So now this is classic, a spring, physics people. Okay, a weight attached to the end of a long spring is bouncing up and down. So here you go. Let's draw a model of this. So you have a spring here. It's a bad spring, and you have some kind of a weight attached to it. Okay, what's happening is it's bouncing up and down, up and down. It looks stationary, like it's just hanging there going up and down. But what is happening to that over time, if you stretch that out, the height, say it starts up here and you let it go, over time, it's going down, and then it's going back up, and then it's going down again, and then it's this is over time. What's the height of the spring over time? Going up and down and up and down and up and down. Okay. This is the whole idea. When you start looking at it, it could be at some awkward spot. It could be right here. Okay. Who wants a model? This is not convenient for you. What you know is sine, cosine, positive sine, or positive or negative sine or cosine. That's what you know. So that's not a positive sine or a negative sine or a positive cosine or a negative cosine. That is something that we do not have a model for. What you have a model for is something that's either at a max, a min, or a middle. Okay, so that's what you're looking for here in the problem. It says its distance from the floor varies sinusoidally with time, right? It's going up and down here. And as you stretch that out over time, what is the height over time? Okay, as time goes on here. Okay. When the stopwatch reads 0.3 seconds, the weight reaches a high point. So now you have a nice high point here. When is that time here that you looked at 0.3 seconds? Okay. And then you know the height and all of that. So let's go graph this now quickly. I'll erase all of this. Okay. So here we go. So quadrant 1, again, draw it so you can see what's happening there. Hello, my eraser getting stuck. Okay, so you have a high point at 0.3 seconds of your spring. So go ahead and draw a wave that reflects a high point first, high to middle, middle to min, min to middle, middle to max again. And it said it was 60 centimeters. So this is the height here. This is your time going in this direction. So it says 60 centimeters above the floor. The low point occurs at 1.8 seconds. So here's what your stopwatch reads here, 1.8 seconds. That means you have half a cycle. Okay, and the low point was 40 centimeters here. So I'll write that down real quickly. So what you need to do is find out the time between, that's just half a cycle there. So 1.8 minus 0.3 would be 1.5 seconds divided by 2. So it's 0.75 seconds in each quadrant. Okay, so 0.3 at the start, that's when you're what you looked at on your clock when is a good spot on your wave, plus 0.75 would be 1.05, plus 0.75 should equal 1.8, which it does, plus 0.75, it's going to be 2.55 here, plus 0.75. This is the end of your cycle, 3.3, excuse me. Oops. Go away. 3 point, go away. Sorry. Here we go. 3.3. 3.3. There we go. Okay. So now we need to find your midline there. So sorry, the phone's ringing. That's always useful. So between the max and the min, 60 minus 40 is 20. That means it's 10 here and 10 here, centimeters. Okay, so what's the middle line going to be? 60 minus 10 is 50 centimeters, right? It's just the average between those two right there. All right, now we can start modeling this equation with a function, this graph. That's the whole point of drawing the graph, so we can write the equation. Again, you are going to have, this is a cosine, a positive cosine function. Okay. So we can go ahead and fill that in. Amplitude is 10. Cosine, and then B can be determined by the period, 2 pi over the period. The period, what is one whole period here? Let's see. So from 0.3 seconds all the way to 3.3 seconds. That sounds like 3 seconds total, right? 3.3 minus 0.3, that's 3 seconds total. That's the period. So it would be 2 pi over 3. Okay, so go ahead and fill that in, 2 pi over 3 for your B number. X minus the start, what's the start? 0.3 plus the vertical shift, which is here, D, 50 centimeters. There you go. So there is your equation, which models the spring. Okay, so don't think too practically about this. We're assuming, like in the Ferris wheel, uniform speed and it's going forever, right? Or for a long time. And same with the spring, not that it's like, slowly, and, the undulations are getting smaller and smaller and it's slowing down. We're just assuming a perfect world where we're modeling a spring that's going up and down for a long time. And we're modeling that, or a fox population, or a temperature, or whatever it is, in a perfect world. Okay. It's not like got a slow startup time and then it's slowly winding down. This is a perfect world where you are just having the spring go up and down between the same max and min forever and ever and ever. Okay, so don't try to think too hard about that. All right, let's try one more example here. Or maybe that was it. I believe I've done all of them now. So thank you very much for watching. Again, if you wanted to find the height of the spring at any one time, you would just put that time into the model you just created, the cosine, and you could find out